All right, so hello everyone, and welcome to this month's SEDS online webinar. As always, we'd like to thank our sponsors from IAS, which allow us to offer all of these resources free of charge. So things like recorded lectures, learning tools, and even virtual field trips. So make sure you take a look at our website to see all the new info. So today's lecture is by Dr. Anne Bernhardt, who is a sedimentologist at Freie University, Berlin. Dr. Bernhardt got her PhD degree from Stanford University, and her research interests include understanding how sedimentary rocks record Earth's history processes across a broad range of temporal and spatial scales to discover how marine, classic sedimentary successions, geomorphology, and terrestrial and marine surface processes work together. So I'll hand it over to you, and thank you for your talk.
Yeah, thank you very much for having me. And today we'll tackle the question of where, and maybe more interestingly, why do submarine canyons develop? And this is a work that I did together in cooperation with my colleague Wolfgang Schwangert. He was close to here at the University of Potsdam. And we are taking a very broad global approach here, which is mostly based on spatial statistics. So most of the methods we use are going to be statistical methods. I tried to make this as accessible as I could, so have no fear. Even if you're not a stats person, you will be able to follow, I hope. See how I change this? Here we go. So the way I set up this talk is I'm going to give a relatively brief and simplified introduction into what we know about submarine canyon formation. And then we'll tackle two research questions. The first is going to be, why do canyons remain connected to the coastline during sea level rise? And we are trying to predict using Bayesian analysis of where that occurs and what the processes behind these would be. And then in the second part, we will broaden the scope somehow, and we are going to try to predict where all other types of submarine canyons actually occur on a global scale. And we will use a slightly different statistical technique here, which is called point pattern analysis. And don't worry if you don't know what that is, I come to this and also explain. And that after that, we will conclude. You can follow up on the bar up here where we are, just in case you get lost on the way. So basically, there are two very general, very simplified end-member hypotheses to how submarine canyons form. And the first one would say, well, submarine canyons incise headward into the continental slope by mass wasting and retrogressive slumping. And then over time, they can erode back towards the shelf and finally indent the shelf edge itself. Now, opposing to this, submarine canyons could form downwards by the erosion of turbidity currents that are sourced either from the continental shelf itself or even directly by river systems. And then the canyon would develop downwards. Now, we are going to try to predict using different topographic and other environmental parameters of where these canyons occur. And if that first hypothesis prevails or dominates, then parameters such as the gradient of the continental slope should be a parameter that controls the distribution of submarine canyons. If the second hypothesis would dominate, then terrestrial parameters, for example, the sediment flux from adjacent river catchment should be more important in the prediction of these canyons. And we will test for this. Now we distinguish between slope confined canyons. So these are submarine canyons that are only confined to the continental slope versus shelf incised canyons, these type of canyons here, and these as well that actually incise into the shelf edge and into the shelf itself. So there has been work done on parameters that control canyon distribution or canyon spacing. For example, there's a geology paper from what's actually my year of birth, 82 from Twitchell and Roberts, and they looked at the New Jersey continental margin and mapped several submarine canyons in here. And they said, well, canyons are numerous, that's clear, we can see that, and their spacing correlates with the overall slope gradient. So you can see that the contour lines here, this is 200 meters and this is 2000 meters of water depth. And where these contour lines converge, the canyon spacing is actually increased. So there are more canyon spacing where that slope is steeper. Now, this is a very qualitative vision of things. It seems to work, but we can actually now test these relationships on a global scale and see whether this relationship holds on significantly on around all continents. There has been 2 recent studies that favor clearly the upward formation of submarine canyons, so that first hypothesis that I showed. And one is from One et al. In geomorphology last year, and they did some stratigraphic forward modeling and susceptibility mapping of the continental slope. And they are concluding that submarine canyons tend to retreat landward. They capture gullies on their way back and form shelf-incising canyons, and that upslope pattern is dominant regardless of changes in fluvial discharge and changes of the initial morphology of the seascape. So they clearly favor this hypothesis, and this has been sort of shown in a 3D seismic reflection data set as well offshore southeastern Australia, where we have big slope failures and that indent the continental slope here, and then these canyons would be confined to these big mass failures working their way upward towards the shelf. So recent studies have favored upward formation. There's more studies out there that would say the opposite, but we want to test, are these processes actually of global importance, and can we go beyond these relatively regional approaches here? But first of all, moving into our first research question, we are going to focus on this particular type of canyons. Canyons can incise all the way back towards the coastline and actually connect to terrestrial sources, to terrestrial sediment sources next to the coastline. These might be either rivers. So this is the Biobío River offshore in south central Chile that connects directly to the canyon head of the Biobío Canyon here. And we want to predict where do these types of canyons occur and how do they remain connected to the shoreline during different cycles of sea level. So basically, to show this, there might be several canyons being connected to the shoreline during low sea level stand, and then during sea level rise. Some canyons actually incise all the way back and still connect to the shoreline after the sea level rise, and some of them might just not make it. And we want to determine what makes the difference here. We are interested in these types of canyons because they are very efficient in routing sediment or organic carbon, pollutants, and litter to the marine sink or to the deep ocean. And this is sort of shown here in this spectacular footage from Martina Pierdomenico. That's a canyon in the Messina Strait in Italy. And you can see that after a flash flood, and this canyon is connected to a river system on shore, that large amounts of litter with really coarse grain sizes, if you will, can be very efficiently transported down this canyon here. This is quite a shocking footage, I would say, during these flash floods. But that means that these canyons are very efficient transport pathways. So there are several controls on submarine canyon occurrence and shelf incision of the same canyons that were suggested in the literature, and I'm just naming a couple of them: narrow continental shelves, high shelf gradients, mass wasting along steep continental slopes. We already talked about that. Submarine groundwater seepage, for example, high sediment flux from onshore. Low erodibility, meaning hard or durable bedrock in the river catchments onshore that then can provide coarse-grained sediment supply that helps eroding the canyon head and the canyon floor. And also wave focusing into a canyon head has been discussed here. And what I think is very exciting is that for all of these, or at least many of these parameters, we do have global data sets now. And so we can actually test these correlations or these relationships on a global scale. And I think this is super exciting and a fun thing to do. And it basically also started out as a Corona hobby for me when we couldn't go into the field. Our approach also accounts for the fact that several of these controls can act contemporaneously, right? We can have either one of these processes acting. So what we did now, we calculated more than 30 predictor parameters and then assigned these to submarine canyon heads. And we divide those into terrestrial parameters, into terrestrial predictors that we calculated. I'm not going to read all of these to you, but they pretty much include catchment size, so river catchment size on shore, the gradient of the rivers, the water discharge, suspended sediment load of these rivers, peak ground acceleration as a proxy for tectonic activity, rainfall, bedrock lithology, and so forth. And then on the marine side, we calculated several parameters, including submarine groundwater discharge from a global model, storm surge height, wave height, and the morphology of the shelf, including shelf gradient and width, and also the gradient of the continental slope. And then we classified a whole bunch of canyon heads on a global scale. So these are canyon shapefiles that have been mapped in a global database by Harris et al. In a paper called Geomorphology of the Ocean. And we basically, and those are large scale canyons that are mapped on a global, relatively low resolution bathymetry. And we assign canyon heads to all of these shapefiles. And then we calculate how close the canyon head is either to the coastline itself or to the minus 120 meter contour line, which means that these might have been connected to the shoreline during the last glacial maximum when the sea level was lower. And then we classified these canyon heads. We disregard the ones that are not anywhere close. Sorry about that. We classify shore-connected canyon heads at the present day, and then we also, for the fun of it, classified canyon heads along the minus 120 meter contour line. So we end up with a whole bunch of points on a global scale. So again, we use the database provided by Harris et al. We restrict our analysis to the main continents between 50 degrees north and 50 degrees south. And out of the 4,600 and something canyon heads that we mapped, we classified almost 800 of these are located at the minus 120 meter contour, but only 183 of these canyon heads are connected to the shoreline during the present day. So the pink ones are the minus 120 meter contour line canyon heads, and the green ones are the ones that actually connect to the shore during the present day. Now, what we do now to reduce the complexity of the data sets, we tile, we use a global grid, and then we count in each tile how many of these types of canyon heads occur in a certain area. So we reduce the complexity a little bit, and this is how this looks. So we tile this. Each tile here has a size of about 50,000 square kilometers. And then we count how many of these canyon heads are actually occurring within each tile, and the numbers color-coded in here. Now, this is the distribution of submarine canyon heads along the minus 120 meter contour. And what you can see is that these are nicely distributed along all major continents, and these actually occur quite frequently. Now, if I now switch to the canyon heads that are connected to the shoreline at present, we can see that these are much less, first of all, and they mostly cluster in 3 spatial hotspots, which is the Mediterranean active margin, the Pacific coast of Central America, and the Pacific coast of Central South America here. And then we have a couple of canyon occurrences scattered throughout in other places as well. Okay, so what we are doing now, our aim is to globally predict the number of present-day shore-connected canyon heads in each tile. That's our target variable. And then we use a bunch of predictors, all the terrestrial and marine parameters that I showed you before, to predict the target variable. And we do this using Bayesian penalized regression. That's a lasso regression. And a lasso regression has the advantage that it uses a penalty term that shrinks very small regression coefficients to 0. And that means that we can remove unimportant predictors. I told you we calculated more than 30 of those. And it's hard to interpret. We really want to get rid of the ones that are not important or do not enhance the model performance. And then we can quantify the importance of each predictor, adopting a predictor ranking algorithm, which has been previously been written. Okay, and these are the results. This is a bit of a busy figure, but I walk you through. So on the x-axis, we see the posterior distribution of the regression coefficients. So these are the regression coefficients. And then on the y-axis, we see these different predictor parameters. They are ranked by importance. They can double rank on, depends on how you set up that algorithm. But rank 1 is shelf gradient being the most important or being the one that mostly enhances the model performance. And if you look at the uppermost ranks, we can see that shelf morphology really dominates these upper ranks. We have shelf gradient here, mean shelf width, and the difference of shelf width between the present day and the last glacial maximum. So shelf topography seems to be very important. And on rank 2 and 5, we find 2 terrestrial parameters. Rank 2 is occupied by the erodibility index, and that is the erodibility of the bedrock in the adjacent river catchments. And what this says is the steeper the shelf gradient, the more of these shore-connected canyons to occur, the less erodible or the less soft or the harder, the more durable the bedrock on shore is, the higher the number of shore-connected canyons that we are predicting. Let's look at how these models actually perform, just to see whether we are doing something useful here. So this upper plot shows the number of shore-connected canyon heads per tile that I explained before in the real world. And then the second plot shows the predictions made by the penalized regression that I also explained. And what we can see is that we relatively faithfully predict the 3 spatial hotspots that I showed before. So we are predicting the Mediterranean canyons, the Pacific coast of Central South America, and the Pacific coast of Central America is quite well reproduced. Okay, so the main spatial hotspots we can actually predict. However, it's always interesting to also look at the residuals or at the parts that we are not doing very well in predicting. And first of all, that would be the Californian coast here, where there are several shore-connected canyons which we are not capturing in the model prediction at all. And I think why that is that we are clearly missing predictor variables in our predictor space, not because we want to, but because we don't have global data sets for them. For example, these Californian canyons have been shown in the literature to be often fed by longshore sediment transport. So they receive a lot of relatively coarse-grained or sandy sediment from longshore transport that then erodes can erode the submarine canyon head and floor. And we don't have a global data set for the volume of sediment being transported this way. So once we have that, we can actually include it in the model and see if we do any better. But for now, we are missing out on those. Now, there are also a couple of canyons along the African coast, which we are not predicting. And these might also be due to missing predictors. I can't really tell you why or which one is missing here. But for example, these could be also longshore transport, of course, but underlying faults that then create zones of weakness that help the shelf incision of the canyon itself. Or there might be shelf-incised fluvial channels present on the shelf that incised there during sea level low stand and are now also zones of weakness that can be reoccupied by canyon incision. So here we don't actually know what that is. Once we had global data sets of, for example, faults offshore, then we could put it into the model and see how we do. Okay, so let's conclude for this first part. High shelf gradients and narrow shelves really precondition the canyon head connectivity to the shoreline here. And on top of that, canyon heads preferentially remain connected to the shoreline offshore rivers that that export or that erode low erodibility bedrock, so hard or durable bedrock, and have a high water discharge. And we think that the process behind this is that such catchments deliver durable or even coarse-grained bedrock. We didn't test for grain size, of course. But that type of material can then efficiently erode the submarine canyon head and floor, such the same way as it has shown to do in bedrock channels in the terrestrial realm. And there's a regional and a local study from Smith et al. In GRL that also hints at relationships at these kind of relationships at a smaller scale. But so we are quite confident that we are at something here. Okay, so this brings us to the second part of the talk, where we zoom out quite a bit still, and we focus on all types of canyons, basically. So we will focus on slope confined canyons that are just incising into the continental slope. And we will also predict shelf-incised canyons, and then the shore-connected one would be within the shelf-incised category as well. And the method that we use for this is spatial point pattern analysis. And that's a statistical technique that tries to identify the underlying mechanism or the underlying process that determines the distribution of points. So now we are treating submarine canyons as points in space, similarly to the canyon heads that we treated as points as well, actually. I just give you a brief introduction into point patterns. So these are points that are somehow distributed in space here, and that could be the spatial distribution of trees, for example, of mineral resources, of cold water coral mounds, bed forms, whatever type of data you might want to treat as single points. And then we are taking predictor variables where we have numerical values in the same space, in the same spatial window. And we see whether we can use these predictor variables in order to predict where these points actually occur. So these are the first order effects that we are testing for. And then there's so-called second order effects, where we can test whether the points themselves can act on one another. So there are three different cases. I know this sounds a little bit dry, but it's going to get interesting when we put this into the canyon space. These types of points are just randomly distributed in space. That's just random. But points might interact on one another in a way that they inhibit one another. For example, if you look at the distribution of trees, and these trees have really big crowns, then the next big tree cannot grow right next to tree number one because it's not going to grow big in the shade. So there will naturally be a certain distance between the different points. And then there can be several processes that cause clustering of these points. So then these patterns might not be related or controlled by some other predictor parameter, but because they are interpoint interactions. And we can also test for this. And then just be with me for a little bit longer for one more method slide. So there's one more complication that we are facing, because we will need to treat our spatial point patterns as a point pattern along a linear network. So what this is, for example, here, these points show traffic accidents along a road network, and I think this is the city of Perth. Now, if you want to model where traffic accidents occur, then these can only occur along the roads, right? They're not going to occur in the outer in the space here. And so that changes the mathematics behind this a little bit, because points can only occur along the network itself. And maybe a more sedimentological or geomorphological application here are nick points along a river network. Of course, nick points can only occur on the riverbed itself. So if you want to model their distribution, then it has to be along the network of the river itself. But why is this interesting for canyons, or why should we treat our data like this? And this is because of the following idea, that we take the same canyon shapefiles. I showed you these before. We are now not mapping the canyon heads, but we are calculating the canyon center points, or the center points of these shapefiles. And now, as you can see, these points cannot just occur anywhere along the continental slope. These white outlines are the continental slope, but there can only be one canyon at a time, or along a stretch of the continental slope, because they cross the entire continental slope, right? So they cannot be randomly distributed here. So what we do is we take the center line of the continental slope, we collapse all the canyon points onto this line and treat this as a linear network. That's just our trick in statistically describing that there can only be one canyon at a time. Okay, so let's get at the real data finally. So we reduced each submarine canyon to one center point on the continental slope. I'm plotting the points here for the main continents. We are again only looking at the main continents. I'm getting rid of islands and such, just for to make it to simplify the data set somehow. And you can already see that Australia seems to have a lot of canyons, and then South or Southeast America not so much. And what we do then is we take a Cornell estimator and smooth over these points, and then we come up with a parameter called canyon density, which is really just how many canyons occur per kilometer along that center line. Okay, so you could multiply this by 100. So 8 canyons per 100 kilometers along the continental slope would be a high canyon density in this case. Okay, so and basically this smooth canyon density with a unit of canyons per kilometer is our target variable. This is what we are trying to predict. We split this into the two canyon types, slope-confined canyons and shelf-incised canyons, as I explained before. And because we also want to test whether there are different predictors that are important when predicting these different canyon types, meaning are there different processes acting behind the formation of each one of the types. Okay. And we take a reduced set of predictor variables. This time I introduced most of these to you already. These are all numerical predictors, meaning that they have numbers to them. And then we use two categorical predictors. First of all, the margin type. So we can categorize these canyons into whether they occur on a passive or on a tectonically active margin as well. Because there has been literature out there that implies that there are different processes acting along each one of these margin types, which is quite plausible, I think. Okay, so what we do then with the predictors, this is the erodibility index of the onshore bedrock. That's a parameter that I mentioned before. And so we calculated the average erodibility for each river catchment onshore, and then we predict the erodibility onto the continental slope, because we need our predictors in the same XY locations than our canyon densities. So we are predicting these offshore to have them at the same, in the same spatial window, so to speak. And then we use these predictors to predict canyon density. And we do that using a log linear function of each predictor at each location. So this is a spatial approach, right? So we predict canyon density at each XY coordinate, at each XY location. And then we calculate for each of the 16 predictors, we calculate the regression coefficients. And I show you the results of the regression coefficient in a second. We reduce the predictor or the number of predictors by stepwise regression because we want to get rid of all the predictors that are not important and just, get left with the ones that actually enhance the model performance or that it say something about how canyons are distributed along the global margins. And a key property of the model is that the points are not interacting. So the canyons are not interacting. Remember the independent and the inhibition and the clustered pattern that I showed at the beginning. We are not going to test for this now. I'm going to do it afterwards and to show you whether there are interactions or not. Okay, let's look at the model predictions first. So this is the real world. This is the actual canyon densities of slope-confined canyons around the major canyons, continents, I'm sorry, and these are the predictions. And when we visually compare this, this actually works surprisingly well. I was very pleased when I saw this. So we are predicting high canyon densities around the continent of Australia, for example. We predict relatively high canyon densities along the US East Coast and also the European Mediterranean. And we can predict much lower canyon densities around Africa and South America. So I think we are capturing the global patterns here quite well. Same spiel for the shelf-incised canyon densities. This is the real world, and these are the predictions. And we are also, I think, capturing at least the hotspots, the northern tip of the Arabian Peninsula, for example. The Mediterranean has high canyon densities, and then actually Australia has very low shelf-incised canyon densities. And the model also captures this more or less. Good. This is also a little bit of a busy slide, but I walk you through. So this plot, on this plot, we are showing two metrics of model performance on each one of the y-axis. And I will probably stick with the pseudo R square here. And this is not the general R square that's often calculated during regression, but a pseudo R square is considered to be good when it's, or excellent actually, when it's between 0.2 and 0.4. So we're not doing excellent here, but I'll get back to the metrics. But what we are doing here, these are different predictors, and we are adding each one of these predictors and see whether the model performs better or whether it's not actually worth it to add yet another predictor. So when we are adding the continental slope gradient, our model performs much, much better than it would do without. Then we add the age of the ocean lithosphere. Now I lost my cursor. The age of the ocean lithosphere, and it's still and it performs much better. And then we add the margin type, whether this is a passive or a tectonic active margin. It becomes a little bit better, but not much more actually. And after that, we actually don't gain much by adding more predictors. So the first three ones, the continental slope gradient, the age of the ocean lithosphere, and maybe a little bit of margin type actually makes a difference. And so we don't actually need any terrestrial parameters to predict the distribution of slope-confined canyons worldwide. Same plot for shelf-incised canyons. We see when we add continental slope gradient, same as here, our model performs much, much better. We add shelf gradient, and it gets even better. And then we add QW, which is the water discharge from the adjacent river catchments, and it gets a little bit better. Keep losing my cursor here. And if we add the shelf width doing the LGM, the last glacial maximum, we still gain a little bit of model performance, but not too much. So these are the most important predictors here that we need in order to predict the global patterns of shelf and sized canyons. So let's just, forget about all the rest and look at the regression coefficients of these important predictors. And for slope-confined canyons, we see that the continental slope gradient has a relatively high regression coefficient. These have been scaled before, so we can use them to say something about the importance as well. And we see this is a positive regression coefficient. That means the higher the continental slope gradient, the higher the densities of these types of canyons. Okay, the older the ocean lithosphere, the greater canyon density. And then this negative regression coefficient says that there are generally less, or the density is less around passive margin than it is around active margin. So we have more canyons on active margins. For shelf and sized canyon, we see the same relationship for continental slope gradient. The steeper the continental slope, the more canyons will occur of either type. The steeper the shelf gradient, the more canyons will occur. And then also the river discharge, water discharge, that is, has a positive relationship. And then the narrower the shelf, so the less wide the shelf, the more canyon densities will occur. That tells you that negative regression coefficient. But we can even do better than this, right? This is a very general tendencies and on how the predictor variable actually relates to where canyons occur. But we can look at the actual relationship as well. So this plot here is for slope-confined canyons, and we are looking at a logarithmic scale of the continental slope gradient down here at the x-axis, and then the canyon density of slope-confined canyons in dependence of the continental slope gradient. And we can see that there's a very nice relationship, basically a power law relationship between these two parameters. So the steeper the continental slope, the higher the canyon densities, the more canyons will occur. Very nice, very clear relationship. And we can say the same about shelf and sized canyons. Okay. So let's look at these types of relationships for the rest of the predictors. So we have slope-confined canyons here, and then shelf and sized canyons here. And the continental gradient we have already looked at, right? We've seen this relationship. The second most important parameter here for slope-confined canyons is the age of the oceanic lithosphere. And here we can see that canyon densities increase until about 70 million years. So until the age of the adjacent oceanic lithosphere is about 70 million years old. But then this, the canyon densities don't increase any further. So next to older oceanic lithospheres doesn't really make a difference anymore. Shelf and sized canyons show also a very nice relationship to shelf gradient, very consistent with our log linear model approach, where we have higher canyon densities at steeper shelf gradients. The other two parameters are actually not that clear. For example, the water discharge here, canyon densities only increase until a water discharge of 7 cubic meters per second. That's not very much, right? So that basically means, well, if it's super dry and there's no water, there's no river discharge whatsoever, then there's also less canyons. But above 7 cubic meters per second, it really doesn't make a difference anymore. This relationship shows that there are less submarine canyons the wider the shelf is, or the wider the shelf was during the last glacial maximum. That also makes sense because it's easier to incise into steeper and into narrower shelves. Good. So first conclusions here. So our models do have some predictive power. We successfully predict the global patterns of canyon densities for both of the canyon types. the metrics of model performance, for example, the pseudo R-square, are not necessarily perfect, right? We come up to 0.08, whereas 0.2 would be excellent. So that's not great. And we think this is because we are missing predictors again. And I mentioned this for research question number one. There are certain predictors that we think are important, but we simply don't have global data for. For example, faults along the shelf or the continental slope that form zones of weakness, or oceanographic conditions such as longshore transport, which we don't have global data for, or shelf-incised fluvial channels that are easy to erode in once they have formed on the continental shelf. So we think the metrics could be enhanced if we were adding more predictors that might be important, but we are simply missing them at the moment. Once we have them, we can include them in the model without problems. Okay, and this is going to be the last a little bit complicated part, and then I guess we are through, because I want to get back at these canyon interactions for just a second. Remember, I said, well, the distribution of points can be, of course, controlled by topographic gradient or other predictor parameters, but also these points may show some self-organized feedback and they act on one another. So this is interesting or important for submarine canyons because there has been a paper published by Daniel Orange in '94, I think, and they show, or they claim that they see very regular canyon spacing along several continental margins, and they say that once a canyon incises into the continental slope, then it affects the hydrologic conditions of the surrounding seascape. And because it's attracting fluid flow and it's increasing the hydraulic head where the canyon incises, then it forms a feedback of fluid flow that induces slope failure processes. And because the incision of one canyon drives away the fluid flow from the surrounding seascape, then the next canyon will not form right next to it, but further on where it can build up yet another higher hydraulic head. So this leads to a self-organized morphology that then ends up in very regular spacing of mature canyon systems. And this would be an inhibition pattern. This would be a regular pattern where points act on another in a way that they inhibit one another. Okay, and we can test whether we see this in the data. And the way we test this, we basically calculate all the distances between all these points, and then we plot the cumulative distribution of these distances, and they are pairwise, right? We do this between every point. And this is relatively easy to read. I walk you through. So the pink pattern is the case where the points are completely independent and they don't interact whatsoever. Then if we see few small distances, so the green line here is below the pink line, so we see fewer small distances in the cumulative pattern, then the pattern shows inhibition, right? Because the distances are rather large and the small distances are not represented in this pattern. Now, if the point pattern is clustered, like here, we have many small distances, and that comes out in this cumulative function as a clustering or as a line that is above the independent line that shows lots of small distances. Okay, so we can test for this visually relatively quickly here. So this is the line for our point pattern, or for this canyon point pattern, and that also accounts for the clustering or the inhibition that we see from, or that we can explain by the statistical model that we have already calculated. So these interactions are in here already, and then we plot a simulation envelope, meaning that this would be the range or the confidence level that we can move in. And we can see that calculated line is actually within the envelope. So we do not see any inhibition, and we also don't see additional clustering. So that means that we don't, on this global, very broad scale, we don't see canyon interactions like the ones suggested by Orange. That doesn't necessarily mean that they are not there. They might refer to smaller canyons that we don't capture in the global data set, or they might be found on a more regional scale within one hydraulic field. Okay, but now let's conclude. So I think point pattern analysis actually holds great potential in geomorphology and sedimentology, because we can use it to understand the distribution and therefore also the formation of landforms, bedforms, ecosystem, you name it. It has been used quite a bit to predict landslides, but it could also be used for pockmarks, sinkholes, mineral deposits. So if you are working with any data that could be modeled as point patterns, please contact me. I'm always interested in new applications, and maybe we can pull something off here. Global submarine canyon occurrence along major continental margins can be predicted by the method that we use, and the density increases mainly as a function of continental slope gradient. So continental slope gradient is the most important predictor for any one of these canyon types. We see no evidence for now for canyon interactions or any self-organized geomorphology here. High slope confined submarine canyon density occurs around high continental slope gradients. I said this several times, but also on ocean margins that are generally older than 70 million years. High shelf and size submarine canyon density also needs high continental slope gradients, but also steep shelves. So we think that by this predictor selection, we can claim that upward of a canyon formation with backwards erosion, so that first end member hypothesis that I showed, dominates, because terrestrial processes really play a minor role here, right? We couldn't really come up with a very important terrestrial parameter such as river discharge or sediment supply. However, when it comes to these shore-connected canyons that I mentioned in the first part, the occurrence is favored also by shelf morphology, narrow shelves and high shelf gradients, but terrestrial Earth surface processes are also important when maintaining the land-to-shore connection. And this is expressed by the important predictors of low erodibility bedrock on shore, so a hard, durable bedrock that can then erode when it's being transported as sediment, and also high water discharge from the adjacent rivers. And as this is an online talk, I'm just going to show the references that I used. The first part we have already published. The second part I thought would be submitted by now, but then life always comes into the way, and I'm actively writing the paper, and it should be submitted relatively soon, I hope, when the semester is over. All right, well, thank you very much, and I'm happy to take your questions.
All right, thanks very much for that talk. It was great. So the chat is now open. So if anybody has any questions, please post them in the chat. To make sure you post them to everyone, and tell us who you are and where you're watching from. So while we wait for some questions to come from the audience, I have one or maybe two. Sure. So what do you want your next parameter to be that you're going to include, if you could pick any of them?
Well, for me, it would be three that I couldn't actually decide for. It would be shore parallel sediment transport, which has been shown along the Californian margin, but also West Africa, for example, to be a very efficient process. I think having a global model of this would be useful for many other things as well, not only this work, but it's a significant source of sediment supply. It's also, it also relates partly to coastal erosion, so it's a very, societally important topic. So I wish we had that, and also a map of shelf erodibility. So how hard or how doable is the bedrock? I mean, it's not bedrock in a plutonic sense, but the shelf sediment actually is, and how easy is it to erode into that? That would be important for the model at least. And then just offshore faults, global map of offshore faults would be great.
Awesome. Hopefully you'll get that soon. All right. So we have our first question from Massimo, watching from Houston, Texas. How effective are slope confined canyons at distributing sediments as sandy turbidite deposits?
This is not necessarily a question that we can solve with the data that we showed. I know there is recent work by the group around Michael Clare, and I forgot who the first author was, but I can look that up. That showed that there are actually relatively frequent turbidity currents in a slope-confined canyon, or in a canyon at least that's very far away from the shoreline. That's the Whittard Canyon, and that was recently published, I think, in Nature Communications. But I have to look that up. I can do so. So easy answer: we don't know, because we can't measure that, or it's very hard to measure, right? You need instruments on the seafloor. But first results from other canyons, from the Whittard Canyon at least, shows that this one is surprisingly active and surprisingly efficient. Whether these were sandy or not, I don't actually know. But there's turbidites happening in these canyons.
All right. We have our next question from Jeff in Denver. Did you examine a sediment caliber or fluvial discharge related to shoreline attached systems, e.g. mud-dominated systems like the Amazon, or cobble and coarse sand discharge like in California?
No, we have this in there, I think, intrinsically, because we have the erodibility of the bedrock on shore. And that means for the Amazon, for example, we have large floodplains in the Amazon, of course, that are made of higher erodibility bedrock, so just soft sediment, right? And if you go along California, where the floodplains are not that wide, but you have lots of actual bedrock, hard outcrop of plutonic rocks, then you should go more into the sandy realm, I would say. We don't know what the exact relationship to this actually is. And I would definitely include sediment caliber in the model if we did have global data, but I just need them on a global scale. Once we take this type of analysis, and we will do so to a more regional scale, where we actually do have the data, of sediment caliber per river, then this would be easily implemented into the model space. But now, for now, just sort of, we sort of use a proxy for this, I would say.
Mm-hmm. All right, our next question is from Sarah in New York City. Thank you for your talk. I'm wondering if your work allowed you to observe the standard distance that slope canyons, not shore-connected canyons, incised inboard from the shelf edge. Did they have a limit in distance that the submarine canyons could headward erode?
I have the data to calculate this. This is a parameter. What I calculated is, let's say, the mean distance of a canyon head to the next river outlet. So these are, distances that I have calculated, but you could calculate the distance of a canyon head to the shelf edge. Right, that's easily done also on a global scale. I also have it set up, so I could calculate that for you if you're actually interested, but I have not done that. And you could, one could look at the distribution of how far these incise, because I think what you might want to get at is we are lumping all shelf incised canyons into one category. But I do think it matters in how far they actually incise back, right? Do they just tip into the shelf edge, or do they erode back further? So this is something that could be quantified, but I just haven't done it.
All right. Our next question is from Val in Aachen. This is amazing work. I guess I have two questions here. One, does the order in which you add your parameters change the quality of the model? Thinking about the slides where you show how the quality of the model kind of reach a plateau after more than 3 parameters. And the second question is, do you expect that your model could predict canyon distribution along, let's say, Pangea or any other continental distribution settings?
First question. So the way I showed this, so the way we are actually getting rid of parameters is we use a stepwise regression. And where you basically add, you start off with all the parameters. It depends on how you set up that stepwise regression. There are several ways of doing it. The way I did it is we add all the parameters to the model and calculate the model performance. Then we throw the first parameter out, and then see if the model performance is worse than before. If it's worse, we take the parameter back in. If it doesn't make a difference, parameter stays out. And so we drop one parameter one by one from the model. So we are not actually adding them one by one. And I know that plot kind of looks that way. And I just basically then ordered the parameters in a way to visualize where I took the ones that actually enhanced the R-square, and I sequenced them. But that's for visualization purposes. That's not how we calculate it. We put them all in, and then we drop one by one. And then there's a second question. If we can predict canyon distribution, sure. If we had the slope of the continental gradient offshore Pangaea plus the slope of the shelf, and even if these are coarse estimates, then we could do it. But we need the predictor variables, the 3 or 4 or whatever important predictor variables for the Pangaea situation in order to predict. Then we could do it.
Yeah, that'd be very cool to know for sure. Our next question is from Rebecca in Calgary, Canada. Thank you for your talk. Did all parameters have the same spatial resolution globally?
No, of course not. We resampled the data. In this case, for the second case, it's a we resampled it to 10 kilometers per cell per pixel, just to also to save computation time, and it's a global approach. So I think 10 kilometers cell size is just fine. So there were they resampled to this to that resolution, but of course they don't come with the same resolution in the first part. You always need to make them fit so you can calculate stuff.
All right. Our next question is from Mohammed in Leeds. Can you infer anything about the maturity of the canyons from this data set?
Somewhat. So maturity depends on how you define this. I would define this as more mature canyons are deeper, wider, maybe more sinuous, and maybe also more incised into the shelf. Right, those would be parameters that I would now name from the top of my head for that quantify canyon maturity. And what can we do? We can do depth on a very coarse scale. Right, the data set that these canyons have been mapped on has a kilometer cell size. So we can do depth, we can do width. Sinuosity, we can debate about the resolution, if that actually gives you something that's usable. And then shelf incision into the shelf, we quantified. So yes, I think that's a yes.
All right. I think that's all the questions we have, and we're right on time to finish up. So thank you very much for your talk. Everybody remember to attend next month's seminar at our regular time, 4 p.m. UK time, where there'll be some student presentations. So I hope to see you all then.